Okay, as a prelude to working toward the nonlinear optical properties of macromolecules, we'll start by looking at dimers. So the goal for the present purpose is to use our Statutory representations and hyperellipsoid representations for intuiting the nonlinear optical properties of dimers of similar chromophores. And it turns out we'll start that with the math first and then use the visualization tools. Mathematically, it's really very straightforward to describe coupling between two monomers that are identical. That you either form some or a difference linear combination of the two eigenfunctions, the wave functions, and those in turn correspond to a vector sum or difference of the transition moments, a sum or difference of the matrices describing Raman or two-photon absorption, and a coherent sum or difference of the hyperpolarizabilities describing the nonlinear interactions as well. In terms of the Statutory representations, this is just vector summation. So if I take the vector sum of this of the first vector and the second vector, then the vector sum gives me the transition moment for the sum state, and the vector difference gives me the transition moment for the different state. Now these are still arrows, and so the corresponding hyperellipsoid, or actually in this case ellipsoid representation, would be just a dumbbell, and the magnitude and direction of the dumbbell indicates the direction and magnitude of the transition moment. Okay, so that's pretty darn straightforward. It's not that much trickier to do matrices, but it's a little bit trickier just to sort of keep track of the bookkeeping. So if we look at these two matrices, if we add them together, you can sort of identify right away what the principal moments are going to be. There's going to be a nice big long green one along the vertical axis, and because these reds are almost similar, there'll be a negative and shorter axis on the horizontal. You can qualitatively get that from this Statutory representations, but of course plugging in the actual numbers and then replotting gives you a much better sense for what the sum and difference actually are quantitatively for the sum and difference state. For the difference state, it's a little interesting. So what I'm really doing is adding this and making this one negative in sign, and making the other one positive in sign, and then adding these together. So if we're adding the red, if this green arrow is now red and this green arrow stays green, then they will largely cancel. The one place where they won't cancel is I'll have a little bit of green here add to a little bit of green there, and that gives us this angle, this double-sided angle arrow at 45 degrees, negative 45 degrees. I'll have a similar argument, in fact it's mirror image, operating on the other side where we've got red now for the double-sided arrow adding to the red on this right side, and that gives us the red component at plus 45 degrees. And so that's the Statutory representation for the different state. And the hyperellipsoid, or in this case, my ellipsoid representation, mirrors the Statutory representation. For the hyperpolarizability, well, it's really just the linear combination of these two processes, the vector sum and difference and the matrix sum and difference, because we generate the hyperpolarizability, the resonant nonlinear polarizability for the individual sum or difference states by the direct product, the Kronecker product of the transition moment and the matrix for either Raman or two-photon absorption. And so we just do the same vector addition and subtraction that we did before for the transition moment, and the same matrix addition and subtraction that we did for the Raman or two-photon matrix, and these are the corresponding Statutory representations for the sum and difference state. And of course, they have their own corresponding hyperellipsoids as well. So does this simple sum and difference work? Let's choose something where it really shouldn't, and then see how badly it fails. And the place where our example that we're going to start out with is a classic one. It's bi-naphthalene. And the reason I say that it shouldn't work very well is that apart from this oxygen right here, this is a completely centrosymmetric structure and should generate no nonlinear polarization for either sum frequency generation or second harmonic generation. So it's really just the breaking symmetry from the oxygen that is a sufficient perturbation to allow any SHG. That, and the fact that once you bind another naphthol moiety onto this particular carbon, it's going to change the nonlinear properties of the monomer as well. And that's not easily accounted for if we just consider binapthol. If we just sort of draw a line through here and cut it off and try and describe binapthol as the coherent, as the sum and difference states for the individual monomers, then we're really neglecting any interaction between the conjugated rings. And so it's a pretty gross approximation, and we sort of don't expect it to do particularly well for binapthol. So if it does even remotely well, then we should feel pretty good about that. So if you then take this and rotate it to the orientation that it would be in the monomer, and take it itself, rotate it around, flip it over and rotate it around to A, and take the coherent summation of A plus B, then what you get is the calculation down here for the just visually represented as a hyperellipsoid. And you know what? They're not terrible. You know, quantitatively, they're off, right? Because the amplitude of this sort of double-sided lobe is smaller relative to these outer lobes than it is in the full quantum chemical calculation. But yeah, it's not bad in terms of getting a general sense for what the molecule is doing. It's not great if you're trying to get a full quantitative analysis, but just as sort of as a benchmark initial starting point for interpreting the nonlinear optical properties, this just simple addition works remarkably well, even in this system where you actually don't really expect it to do particularly well. Now, again, I mentioned we can break this up based on symmetry into A and B states. So the A states we know are only Z polarized, where Z is the C2 axis. So those only can have a transition moment component along the Z axis. And the B states have mu X and mu Y. In other words, they have transition moment components along the X and Y coordinates. And so those are just using that one separation along with the character table, you can group out which tensor elements are either forbidden entirely in a system with C2 symmetry, or contribute only to the A sum state or to the B difference state. Now, we don't know necessarily which of those two states is higher or lower in energy, but that's okay. We have other ways of tracking that down. What we're really focusing on right now is the polarization dependence. And here it's really not bad. If you look at the polarization dependence of the A state, again, it's qualitatively very good. There's a little bit of a quantitative difference between the simple trivial symmetry additive prediction and that of the calculations for a fully coupled system. But in both the A state and B state system, you get a pretty good sense generally for what the nonlinear optical properties of the coupled states are likely to be without even having to run a calculation on the fully coupled system. So let's compare and contrast a little more interesting system in terms of as a stepping stone toward proteins, and that is a dimer with two amide groups. So here's one amide group and here's another amide group. And the amide group forms a basic linkage between amino acids and a protein. So in terms of the protein backbone response, this is a reasonably good architecture for predicting that response by coherent summation of each of the individual amide contributions. So how good of an approximation is considering this fully coupled system as just the sum of the two uncoupled monomers in terms of the amplitudes and polarization dependences. And what you see over here in the table, it's really sort of a curious table with calculated and predicted. The predicted are generated by taking the nonlinear optical properties of an individual monomer and then adding it to itself in the orientation of the dimer. And then the calculated is a full calculation of the full quantum chemical calculation of the fully coupled system. And as I alluded to for binapthol, overall there's remarkably good both quantitative and qualitative agreement between the predictions of this really just almost trivially simple symmetry additive approach and what you get from a full quantum chemical calculation. So this is good because it provides an intuitive and simple starting point for interpreting the polarization dependence of coupled systems, where we don't necessarily have to run full, high, expensive quantum chemical calculations on a fully coupled system, but instead can model it as the coherent addition of a number of the monomers, then subsequently separated out into different symmetries based on the orientations based on the transition moments and the symmetry allowed elements for each of the exciton states.